Welcome back to practical session 16 on time constants. So we're going to have a look at the time constants for an RC series circuit, a capacitor and a resistor. We're going to confirm that the universal time constant chart, which we'll have a look at, how long it takes for the current to reach its steady state value and how long it takes for the voltage to reach its maximum value as well. That's the skill practical. That's the circuit you'll be wiring. So what I've done, I've drawn out a circuit diagram similar to the one in your module books. So the supply voltage I'm using is 30 volts into a switch, into a 68 k ohm resistor, through an ammeter, in series with a 100 mic capacitor, and back to the negative of the power supply. So the first thing we can work out, now that we know the resistance and the capacitance, we can work out the time constant of the circuit. As per the equation data sheets or your formula sheets, torr is equal to the resistance times the capacitance. Let's do that. So torr is equal to 68k times 100 mic is equal to 68k times 100 mic, 6.8 seconds. Remember, torr is in seconds. So therefore, the time constant of this circuit is 6.8 seconds. As we've discussed, or as you've learnt throughout this module, what is time constants? How long it takes for the circuit to reach its steady state value. Here I've got the universal time constant curve. So we've got curve 2. Curve 2 is representing the current flow in the circuit. So as we can see, after 5 time constants on curve 2, the current is effectively zero. It's always going to be 63.2% of what's left over, but the fact is we'll call it effectively zero. So after 5 time constants, there'll be no current flow in the circuit. Curve 1 is the voltage curve across the capacitor. So after 63.2%, okay, or after 1 time constant, we get to 63.2%. And after 5 time constants again, we get to the maximum of the steady state value of the circuit, which will be the supply voltage across the capacitor. As we can see in the breakdown, in the percentages here, after 1 time constant on curve 1, 63.2% of the supply voltage. That will be across the capacitor. After 2 time constants, it'll be 86.5% of the voltage. After 3, 95, and after 5, 99.3. Curve 2, which is the current in the circuit, after 1 time constant, the current will be at 36.8% of the total current, and then that'll decrease down to 0.7% of the total current. We use obviously time constants in many different circuits, which your instructor will go through with you. So, what is going to determine the current flow of this circuit? The only thing that's going to determine current flow of this circuit is the value of resistance, because that switch on, when we switch this switch on, the only thing that limits the current is the resistor. The capacitor looks like a short circuit. So maximum current flow will flow at switch on. So what is the current? I is equal to V over R, which is equal to 30 volts divided by the resistance of 68k. 30 divided by 68. K is equal to 441 microamps. So 441 microamps, that's how much current will flow at the instant of switch on. So after 1 time constant, we'll have a look at current, we'll do all the calculations with current and voltage to start with, but after 1 time constant, the current will be 36.8% of that value. So after 1 time constant, which is 6.8 seconds. So after 1 time constant, current will be 36.8% of 441 micrograms, which is going to be equal to, we've already got the calculator, 441 times 0.368 is equal to 162 microamps. 162 microamps. and so on and so forth. Obviously, we won't go through the extended part of this, but you can do this up to 2 time constants, up to 3 and up to 4. And this is what you're supposed to prove in your practical session. So we'll have a look at after 1 time constant, will the current be 162 microamps. The other thing we'll have a look at is the voltage across the capacitor. Well, after 5 time constants, the voltage across the capacitor should equal approximately 30 volts. So 5 time constants, what will 5t is equal to 6.8 seconds times 5 is equal to 6.8 times 5, 34 seconds. 34 seconds. So after 34 seconds, the voltage across capacitor will equal 30 volts. Or thereabouts. Obviously, hopefully you have discussed this in class, but there is loading on the meter. Obviously the meter's across that, and there's some losses in the capacitor. Approximately 34 seconds, the current should be 0 amps, okay? This is after one time. And the voltage across the cap will be equal to 30 volts. So there's 2 things we want to prove here. And I've already wired the circuit, so it's no time wasted there. So curve 1 is the voltage, and curve 2 is the current. Let's look at curve 1 to start with. So we'll turn the Prac on, have a look at curve 1. So what I'm going to show you is the instant it switch on. You're going to see, which is 100% on curve 2, instant it switch on, we're going to see approximately 441 microamps. Now, to show you where that is on the meter, I'm plugged into the 500 scale. So 400, I'm reading the middle scale here, 0 through to 500. So 441 should be, obviously the 400 marks there. So 41 should be, just around the 400. It's pretty hard to tell. But you'll watch that, the current decrease, and then after 1 time constant, which I'll prompt you via the stopwatch here, which will be after 6.8 seconds, it'll be 160. So when this stopwatch gets to 6.8 seconds or thereabouts, let's see if the current is around the 150 mark, which should be about here on the panel meter. And as you can see, the circuit's wired. It goes from the power supply to a switch, through a resistor, and that resistor is a 68k, into the positive of the ammeter, out of the ammeter, into the capacitor, from the negative of the capacitor, back into home. Okay, and I've already put the power supply on 30 volts. So I've got 30 volts there. So I'll turn them both on together, and we'll see if we can see 2 things here. The current jump up to 440 microamps or thereabouts, and then after 6.8 seconds, see if it gets down to 162 microamps. And then after 35 seconds, 34 seconds, the current should be pretty much at 0. Okay, ready, set, go. Here we've got it decreasing, we're almost at 6 seconds. Now, so we're about 150 something microamps. Up to 2 time constants, it's going to be 13.5% of the time. 17, 18, and we said about 34 seconds. So we're coming up now, as you can see the currents, hopefully we've still got that in picture, the current slowly decreasing, reaching its steady state value. Exactly the same as this curve. And obviously you're expected to plot these different points up to 1, 2, 3, 4 and 5. It's normally a team exercise. And there we got it. I'll just stop that, obviously. Okay, so sorry I didn't stop at the right point, but you can see there's no current flow, and hopefully you caught the screen grab there around 34, 35 seconds, the current flow would stop. So I'll turn that off. What we'll do, we'll just make sure that the power's off. I'll turn it off up here. We're going to short the capacitor out because the capacitor is fully charged at 30 volts. So there's a couple of different ways of shorting that out, obviously with a resistor, a lamp, or because it's only nominal current here, microamps, you can just do it with a jumper lead. So make sure that's shorted out. With the power off, most important, with the power off. Okay. The next thing we're going to do is we're going to have a look at the voltage, okay, which is curve 1 on the universal time constant. So after 63.2% of the time, one time constant, which was 6.8 seconds. The voltage across the cap, well, after 5 is going to be 30. So what's it going to be after 1? Let's work that out. So what have we got? 63.2% times 30 volts is after 1 torr. Is equal to, back to the calculator, so 0.632 times 30 volts, 18.96 volts. I'll do number 2 for you. After 2T, it's going to be equal to 2T, 13.5%. Curve 1, try again. So back into here, my mistake. Curve 1, after 2 time constants, 86.5% of the total value. So 2 time constants is 86.5% times 30 volts is equal to 0.865 times 30, 25.96, 25.95 actually, volts. That's after 2T and 1T, and then we'll just do the last one after 5T, which will be 30 volts. So 5T approximately equal to 30 volts. We'll check that out. So we'll check 3 things out here. So this is the seconds on this one is going to be up to 6.8 seconds. 6.8 seconds. And 6.8 times 2. 13.6. I'll give you 2 triggers on this one here. Hopefully we can screen grab that. 6.8 and 13.6 seconds. We'll see if that's 18 or 19 volts. And then after 13.6, 26 volts. And after around 5 seconds, which is 34 seconds, the voltage should have reached its maximum value. Okay. As per the chart. Same thing again, I'll reset that. Okay. Now I've got to turn the voltmeter on, of course, and put it across the capacitor. So it's just growing a bit in voltage here. Okay. Ready, set, go. After 6.8, now 18 volts. Second one was 13.6, now 26 volts. And the next one was 34 seconds. We're looking for 30 volts. 24, you can see it's growing. 34, we're almost there. 33, 34. Now, it's around 29 volts, sorry. I'll turn that off. So hopefully this practical demonstration has proven the theories you've discussed in class. The voltage charges up to a maximum after approximately 5, the current decreases to a minimum, and any point along those curves you can plot knowing the value of the R and C. Thus concludes the practical on time constants.